An object flying at 78,000 miles per hour just slammed into the moon, creating a massive flash of light, visible from Earth at 240,000 miles away.
Something just crashed into the moon, and it was caught live on camera, and the moment people heard about it, the first question was, could this be 3I Atlas? And the answer is no, it's not. But what actually hit the moon is still pretty interesting, and it tells us something important about what's constantly bombarding the lunar surface while we're not watching. So let me show you what happened, and why astronomers are still talking about it. What actually hit the moon. The impact happened on December the 12th, and an astronomer in Ireland was watching the moon through a robotic telescope when a flash of light appeared on the lunar surface and disappeared in less than a second. And this is extremely rare because most lunar impact flashes are only discovered later when someone reviews telescope footage frame by frame looking for anomalies. But this one was seen as it happened live, which is something even experienced lunar observers might never witness in their entire careers. And there's something almost unnerving about watching it happen in real time, because you're seeing an object that's been traveling through space for potentially millions of years, and at this one specific moment it reaches the end of its journey by slamming into the moon at hypersonic speed. The entire event from first contact to vaporization takes less than 1 second, but in that fraction of a second, enough energy is released to create a flash visible from nearly 400,000 kilometers away. The timing was perfect for detection because the impact occurred during the new moon phase, when the moon's surface is mostly dark and unlit by the sun. And that darkness is critical because if this had happened on the sunlit side of the moon, we would never have seen it. The flash of the impact would be completely washed out by reflected sunlight, and it would be invisible from Earth. But because it hit the dark side, that brief burst of light stood out clearly against the black lunar surface. And the object that caused this flash was tiny, probably only a few centimeters across, maybe the size of a golf ball or a small rock. But it was traveling at around 35 kilometers per second, which is about 78,000 miles per hour. And at that speed, even something tiny carries an enormous amount of kinetic energy. When it slammed into the moon, all that energy converted instantly into heat and light, creating a flash bright enough to be seen from Earth 384,000 kilometers away. The impact location was traced to an area slightly northeast of the Langris crater, which is a prominent feature on the moon's near side, and determining the exact coordinates takes time because astronomers have to account for viewing geometry and timing precision and potential instrumental effects. But based on the telescope's orientation and frame-by-frame analysis, they were able to narrow it down to a specific region. Now, here's what makes this scientifically valuable. The timing lines up perfectly with the Geminid meteor shower, which runs from early to mid-December every year. The Geminids are one of the most intense and reliable annual meteor showers, and they're known for producing fast, bright meteors that light up Earth's atmosphere. And what makes the Geminids unusual is their origin, because most meteor showers come from icy comets that shed debris as they pass through the inner solar system, but the Geminids come from something different. The source is an object called 3200 Phaethon, and it behaves more like an asteroid than a comet. It's a rocky object that orbits the Sun, and as it gets close to the Sun's heat, it sheds small particles of debris, and over thousands of years, that debris has spread out along its entire orbital path, creating a dense stream of particles. Phaethon itself was only discovered in 1983, when NASA's infrared satellite IRAS spotted it, and at first astronomers thought it was just another asteroid, but then they realized its orbit matched perfectly with the Geminid meteor shower, and that's when they figured out this rocky object was somehow producing meteor streams like a comet. And we still don't fully understand how Phaethon creates this debris, because it doesn't have the volatile ices that would sublimate and release particles the way a traditional comet does. The leading theory is that extreme thermal stress from passing so close to the Sun causes the surface to crack and break apart, releasing small fragments. Or maybe Phaethon is actually an extinct comet that used to have ice but lost it all over millions of years of close approaches to the Sun, and what we're seeing now are just the rocky remnants still slowly disintegrating. And every December, Earth passes through this stream and we see Geminid meteors burning up in our atmosphere, creating those bright streaks across the night sky. But Earth isn't the only body that passes through this debris field, and the Moon travels through the same region of space, which means it's also getting pelted by Geminid particles. The difference is, Earth has an atmosphere that burns up most of these particles before they reach the ground, but the Moon has no atmosphere, so every particle, no matter how small, hits the surface directly at full speed. And that's what we saw on December the 12th, a Geminid meteoroid slamming into the lunar surface. The estimated impact speed of 35 kilometers per second is consistent with typical Geminid velocities, which strongly supports the connection. And while we can't say with 100% certainty that this specific particle came from the Geminid stream, the timing and speed make it the most likely explanation. And this is only the second documented lunar impact flash ever recorded from the British Isles, and the first one captured from Ireland specifically, which tells you how rare these observations are. The Moon is constantly being hit by small objects, but most of those impacts happen on the far side where we can't see them, or they happen during the day when the sunlight makes flashes invisible, or they're just too small and dim to detect from Earth. So catching one live is a big deal, and it gives scientists a direct, real-time measurement of an impact event, which is data you can't get any other way. Why? Moon bases are in danger. Now you might be thinking, okay, a tiny rock hit the Moon, so what? And that's a fair question, because on the surface this seems like a minor event. But lunar impact flashes are actually really important for understanding what's happening in near-Earth space, and how often objects of different sizes are colliding with planetary bodies. The Moon is basically a giant impact detector, and because it has no atmosphere and no weather and no geological activity that would erase craters, it preserves a complete record of everything that's ever hit it. Every crater on the lunar surface represents an impact event, and by studying those craters, scientists can reconstruct the history of bombardment in the inner solar system going back billions of years. But there's a problem with only studying craters, and that problem is size. Large impacts that create big craters are rare and easy to study, but small impacts that create tiny craters, or no visible crater at all, happen constantly, and they're much harder to detect. And this is where impact flashes come in, because they allow scientists to detect impacts in real time, even when the impacting object is too small to leave a crater that would be visible from Earth. By measuring the brightness and duration of the flash, scientists can calculate how much energy was released in the impact, and from that, they can estimate the size and velocity of the object that caused it. And when you combine these measurements across many observations, you start to build a statistical model of how often impacts of different sizes occur, and that's valuable information. For example, we know that large asteroid impacts that would cause global catastrophes on Earth are extremely rare, maybe once every few million years, but smaller impacts happen much more frequently, and the smaller the object, the more common the impacts become. There's a power law relationship where if you go down one order of magnitude in size, the impact frequency goes up by roughly 2 orders of magnitude. So if kilometer-sized asteroids hit Earth once every million years, then 100-meter asteroids might hit once every 10,000 years, and 10-meter objects might hit once every 100 years, and meter-sized objects might hit multiple times per year. And this pattern continues all the way down to tiny meteoroids, like the one that hit the Moon, which are hitting constantly. And understanding this distribution is critical for assessing impact risks both for Earth and for future space infrastructure. NASA and other space agencies are actively working on planetary defense systems to detect and potentially deflect hazardous asteroids, and accurate models of the impact frequency are essential for prioritizing which objects to track and which ones pose the greatest risk. But there's another reason why lunar impact monitoring matters, and it has to do with future plans for sustained human presence on the moon. Multiple space agencies, including NASA and China, are planning to establish permanent bases on the lunar surface within the next decade. And these bases will include habitats and scientific instruments and communication systems and solar panels, and all of that equipment will be exposed to the lunar environment. And one of the hazards of that environment is micrometeorite impacts. And while a single impact from a centimeter-sized object isn't going to destroy a habitat, it can damage sensitive equipment, and over time, the cumulative effect of many small impacts can degrade solar panels and erode surface materials, and create dust that interferes with mechanical systems. NASA's Artemis program is planning to land astronauts at the lunar South Pole, where there are regions of permanent shadow that might contain water ice, and that ice could be used for drinking water and for producing oxygen and hydrogen fuel. But those same shadowed regions also make impact monitoring more difficult because you can't see flashes in areas that are already dark from shadows. So engineers need to understand the baseline impact rate in those regions and design protective systems accordingly. The Chinese space program is also moving forward with plans for an international lunar research station that would be built in phases starting around 2028. And this would include pressurized habitats and power systems and rovers and robotic construction equipment. And all of that infrastructure needs to be designed to withstand not just the radiation environment and the temperature extremes, but also the constant rain of micrometeorites that will be sandblasting everything on the surface. So understanding how often these impacts occur and with what energies is essential for designing protective strategies. Engineers need to know whether they should be building radiation shields or debris shields, or both, and how thick those shields need to be, and what materials work best. And the only way to get that information is through systematic monitoring of actual impact events, like the one captured on December 12th. There's also the possibility of follow-up observations from lunar orbit, and NASA has spacecraft like the Lunar Reconnaissance Orbiter that's constantly photographing the moon's surface at very high resolution. In some cases, scientists have been able to match observed impact flashes with fresh craters that appeared in LRO, images taken before and after the impact. And even when the crater is too small to see the absence of a visible crater, helps refine the size estimates for the impacting object. And each confirmed impact adds to a growing database of lunar impact events that scientists use to validate and improve their models. Over the past 20 years, systematic lunar monitoring programs have detected hundreds of impact flashes, and that data has significantly improved our understanding of the meteoroid environment in near-Earth space. What's constantly hitting the moon? So, the Geminid impact on December the 12th was just one event, but it's part of a much bigger picture of ongoing bombardment that most people don't think about. The moon is getting hit all the time by objects ranging from tiny dust grains to multi-ton boulders, and it's happening constantly, whether we're watching or not. The vast majority of these impacts are far too small to produce detectable flashes, and they're caused by micrometeorites that are smaller than a grain of sand. These particles are everywhere in space, and they're constantly raining down on every airless body in the solar system, including the Moon and Mars and asteroids. On the Moon, these micrometeorites hit at speeds ranging from a few kilometers per second up to 70 kilometers per second, depending on the relative velocities and orbital geometries. And even though each individual impact is tiny, the cumulative effect over millions of years is significant. This process is called space weathering, and it's responsible for breaking down surface rocks into fine lunar dust and creating the regolith layer that covers the moon. Every rock on the lunar surface is slowly being pulverized by billions of tiny impacts, and that's why the moon is covered in a layer of powdery dust, several meters deep in some places. But occasionally, larger objects hit the moon, and these are the ones that produce detectable flashes. During major meteor showers, like the Geminids or the Perseids, the impact rate goes up significantly because the moon is passing through dense streams of debris left behind by comets and asteroids. And scientists have been able to correlate increases in lunar impact flash detections with the timing of these meteor showers, which confirms that the moon is being hit by the same particles that create meteors in Earth's atmosphere. And here's something that doesn't get talked about enough. Some of these impacts are violent enough to eject material from the lunar surface that escapes the moon's gravity entirely and goes into orbit around Earth. These lunar meteorites eventually fall to Earth, as meteorites and scientists have recovered dozens of them and confirmed their lunar origin by analyzing their composition and comparing it to samples brought back by the Apollo missions. So, in a weird way, the moon is constantly being sandblasted by space debris, and occasionally chunks of that sandblasted material make their way to Earth. And we're finding them in Antarctica and in deserts where they stand out against the surrounding terrain, and each one is a free sample of the moon delivered to us by impact processes. But it's not just meteor showers that pose a risk, and there are also sporadic impacts from random objects that aren't part of any known stream. These could be fragments from asteroid collisions, or debris from old spacecraft, or even small asteroids on eccentric orbits that happen to cross the moon's path. And because we can't predict when or where these sporadic impacts will occur, the only way to detect them is through continuous monitoring. And that's why programs like the one that captured the December 12th impact are so important. By keeping telescopes pointed at the moon night after night, these monitoring programs are building up a statistical dataset that tells us how often impacts of different sizes occur, and whether the impact rate is changing over time, and whether there are any patterns or anomalies that we need to understand. There's even been discussion about establishing a permanent impact monitoring network on the moon itself, with cameras and seismometers placed at multiple locations across the surface. This would allow scientists to detect impacts on the far side of the moon, which we can't see from Earth, and it would provide much more detailed data about impact energies and frequencies. But that's probably decades away, and for now, we're limited to ground-based observations from Earth. And as for the specific object that hit the moon on December the 12th, it's probably been vaporized. At 35 kilometers per second, the impact energy would have been enough to instantly melt and vaporize both the meteoroid and a small amount of lunar surface material. What's left is a tiny crater, maybe a few meters across, that will sit on the moon's surface for billions of years, slowly accumulating more impacts on top of it until it's eventually erased by the relentless process of space weathering. And thousands of years from now, when humans are living on the moon and studying its surface in detail, someone might find that tiny crater and analyze the composition of the ejected material and figure out that it came from a Geminid meteoroid that hit in December 2025. Or maybe they won't, because by then there will be millions of newer craters on top of it, and this one event will just be another data point in the long history of the moon getting pummeled by space. And as for 3I Atlas, it's currently in the constellation Leo, about 270 million kilometers from Earth, moving away at 67 kilometers per second, and it's not going to hit the moon or Earth or anything else. It's on a trajectory that will take it past Jupiter in March 2026, and then out of the solar system entirely and back into the void of interstellar space where it came from. So if you were worried about that, you can stop worrying. The thing that hit the moon was just a Geminid meteoroid doing what Geminid meteoroids do every December. So here's a question for you. If you could watch any object hit the moon live through a telescope, what would you want to see? A massive asteroid that creates a crater you could see from Earth? Or would you rather catch one of these tiny Geminid impacts that happens every year? Let me know in the comments because I'm curious what you think. And if you want to see more videos about space mysteries and weird objects flying through the solar system, hit that like button and subscribe because we've got a lot more coming.